Welcome to class. In this video, we'll consider the formulation of the Taylor series and how that links up into what we call the generalized Cauchy integral formula. Now, this is very important. Why? Because this would form a connector to a very important segment that we are going to be getting to very soon, and that is the Laurent series. Now, before we get to do the Laurent series, it's important to understand what happens on the positive side with something very popular, which is the Taylor series. Now, we would be formulating the series notation of the Taylor series, but this time around from a complex analysis standpoint. So what exactly do I mean? We'll go through the formulation process and see the entirety of the structure of the Taylor series and how that links up into the generalized Cauchy integral formula. As always, make sure to like, share, and subscribe, and turn on notifications so you do not miss any of our videos. So let's begin. Now, the very first thing we want to do is state some important premises that we need to have. The very first thing is we need for f of z to be analytic on the open disc. Now, how exactly is this open disc defined? We have it defined such that absolute value of z minus z naught is less than r, where r is some radius for that open disc. Right? Now, we would also define z here as a point within this disc. Now, on this disc now, we would now, remember we have created the analyticity of the function on the open disc, which is with a radius r. We are picking z to be any point within that disc. We will then create a positively oriented circle of a radius, let's say rho, that will contain that z as well and would be within the open disc with a radius r that we have. So the new positively oriented circle we are creating will now be contained within this open disc. So let z be any point in this disc and select t to be the positively oriented circle of radius let's say rho in this case. Now, this is very interesting as far as this is concerned. Now, the very first thing you'd realize based off this notation is that this positively oriented circle, as I said earlier, is contained within the open disc, right? And then the point z is contained within the positively oriented circle that is contained within the open disc. So it means that if we were to relate that, we would have the absolute value of z minus z naught will be less than rho, which would be less than r. This would be the notation. Now, if this is clear, right, then it means that if we now select another point S within this circle, this positively oriented circle C, we would have immediately that we can relate this point, this arbitrary point, with the point Z within the positively oriented circle, in the sense that one thing that is very clear that would happen is that the difference between Z and Z naught will definitely be lesser than the difference between S and Z naught. And this is very important to keep in mind. Now, why exactly can we say this will happen? Because remember that Z, we have said, is any point in this disc that is still completely contained within the positively oriented circle. It's somewhere interior to the circle. And then we have C that is on the circle, which means it bears a much more distance to z naught compared to z, which is closer to c naught because it's interior to the positively oriented circle. So it's closer to z naught compared to s. And therefore, the distance between z and z naught is going to be less than the distance between s and z naught. Now, if we utilize this, what it would mean is that if we have the fraction 1 divided by s minus z, what we'll see happen immediately is that we can split this denominator and rewrite it as 1 over s minus z naught minus z minus z naught. We see that this balances out. They are exactly the same thing. But more importantly, this notation shows us that this denominator remains positive. The goal of the Taylor series, and in essence, when we get to the Laurent series, is always to ensure that we have a positive denominator. At all times, we are always seeking to have a positive denominator. Now, we have generalized and created this positive denominator. We now want to transform it into a series. How do we do that? Remember that if you consider your knowledge in geometric series and the sum to infinity of a geometric series, you will remember that you can easily rewrite the series form whenever your denominator starts from 1. We are going to be utilizing that same process in this case. Now, how exactly are we going to do that? The very first thing I'm going to do is I am going to factorize 1 out of the denominator, such that if I factorize 1 out of the denominator, the most important thing that happens is I get to have a formulation of this that starts from 1. Now, how would I do that? I'll just take 1 divided by s minus z naught out, and what's going to be left is going to be 1 divided by 1 minus z naught divided by s minus z naught. This is what I would have inside. Now, if you look at this, what is important, or what this, of course, shows us is that, first and foremost, for this bracket, the first term is going to be 1. And then, because, of course, think about it, we are comparing it to a divided by 1 minus r, which is, of course, the sum to infinity of a geometric series. And we're comparing it to that. So it means the first term is 1. And then the common ratio is this guy. Now, of course, remember, you know that the sum to infinity of a geometric series will only exist when the absolute value of r is less than 1. Now, let's see if that is true. Remember, we have said that z minus z naught is strictly less than s minus z naught in absolute value, which means by the time I divide through by s minus z naught, absolute value of z minus z naught divided by s minus z naught will be less than 1. And they are in absolute value. So it means it works perfectly. So I would say clearly that since, of course, absolute value of z minus z naught divided by s minus z naught is, of course, less than 1, then it means I can write this as a sum to infinity, and it would be a valid sum to infinity. What does that mean? It means that 1 divided by s minus z can then be written as 1 over s minus z naught summation j starting from 0 to infinity of z minus z naught divided by s minus z naught all raised to the power of j. And this would be a very, very valid sequence or series. Sorry. Now, also, because, of course, the absolute value of z minus z naught divided by s minus z naught is strictly less than 1, we know that the series exists. It is convergent, which is, of course, the basic premise behind geometric series. It's convergent. The convergence is uniform, which means that by that regard, since the convergence is uniform, I can integrate as necessary. Now, before I do that, I would want to bring this back into the summation, which means, of course, I can write this as 1 divided by s minus z equals summation j starting from 0 to infinity z minus z naught raised to the power of j divided by s minus z naught raised to the power of j plus 1. And there we go. Now that I have this, I can now integrate both sides as I said. And then if I do so, right, what I notice is my integration, of course, of the function f of s in this case, because I am dealing with s on the positively oriented circle. I would now have that the integral, right, the integral over c of f of s divided by s minus z ds would now be equal to the summation, starting from 0 to infinity, of course, of the integral over c of f of s divided by s minus z naught j plus 1 vs and then multiplied outside by z minus z naught j. Now, why can't we bring this outside? Because the integral is on s, right? So the z part can come out of the integral without issues. Now, remember that I can rewrite the integral as such, or I can simply rewrite it based off the Cauchy's second integral theorem, right, which of course introduces the 1 over 2 pi I, so that this will now be equal to f of z, right? Now, if I do so, what would I have? Since I can say that since f of z equals 1 over 2 pi I integral over c f of s divided by s minus z ds, then if I multiply both sides by 1 over 2 pi I, what am I going to have? It will follow immediately that 1 over 2 pi I integral over c f of s divided by s minus z ds will be equal to summation j starting from 0 to infinity 1 over 2 pi I integral over c f of s divided by s minus z naught j plus 1, right, ds multiplied by z minus z naught j. So if I bring this together, what would I notice? I've noticed that first and foremost, the left-hand side, of course, by the Cauchy's second integral theorem, is a representation of f of z, as we've said. And then the right-hand side is a series form, which means I have created a series representation for f of z. And that is quite interesting. And if that's the case, if I rewrite this integral by a coefficient, then it means I can rewrite this as summation, just starting from 0 to infinity of tj z minus z naught raised to the power of j, of course, with the added condition that z minus z naught is less than r, so it's within the region, of course, is within the open disk, where Cj equals 1 divided by 2 pi I integral over c f of s divided by s minus z naught j plus 1 ds. This is going to be the value of the coefficient. And this is very, very important. This, my friends, is the representation of the Taylor series that we are so familiar with right now. So what does this mean? It means by taking clear representation of what happens to an analytic function within an open disk, we can represent that function as a series notation, right? We can represent that function as a series notation. Now remember that in creating this, we have restricted ourselves to the fact that, number one, we are dealing within an entirely positive part of the region, right, which is on the positive end from 0 to infinity, right? Know that in practice, as far as complex analysis is concerned, we do not limit ourselves as such. What happens to the negative parts of the real line, or of the complex values, that is from minus infinity to 0? Would we be able to obtain coefficients based off that? The answer is yes. And in doing that, right, we of course extend our discussions into what we call the Laurent series later on. However, for now, this contains exclusively the Taylor series formation. In the next video, we will consider how this Taylor series now extends into what we now call the generalized Cauchy integral formula, and how we can draw parallels between the two of them. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.